Bell's theorem is decoupled from the physics of quantum entanglement. In literature, Bell's theorem has become synonymous with quantum entanglement. Terminology such as Bell pairs is very pervasive. What people doesn't know, and those who know choose to ignore, is that the physics of quantum entanglement, that is to say, the probability amplitude and the probability of quantum entanglement, was done by Pryce and Ward in 1947. That is 17 years prior to Bell's theorem. Quantum entanglement experiments using gamma-ray photon pairs confirming the Pryce and Ward prediction were conducted in 1948 and 1950 by Hanna and Madame Wu, respectively. Indeed, as stated in 2000 by Delitzsch and Duarte, already in 1948, experiments agreed with quantum mechanics, not with local realism. For a detailed description on the physics of quantum entanglement, refer to Fundamentals of Quantum Entanglement, published by the Institute of Physics in 2022. Jean-Claude Ward utilized heuristic conservational physics to derive the probability amplitude of quantum entanglement. This probability amplitude then was applied to calculate the correct quantum probability for the entanglement experiment of gamma-ray quanta moving in opposite directions. And that was done in 1947. In 2013, a transparent and direct derivation of the quantum entanglement probability amplitude was done from n-slit interferometric principles using the Dirac-Feynman interferometric principle. Observation of that physics immediately shows that Bell's theorem is completely unrelated to the physics of quantum entanglement. Vice versa, anyone who has studied Bell's paper and the derivation of Bell's theorem can see that the derivation of Bell's theorem is completely independent on the physics of quantum entanglement. In fact, the quantum entanglement probability comes at the very end, it's introduced at the very end in a ad hoc fashion into the probability inequality derived by Bell. This is not to say that Bell's theorem is unimportant. In fact, it is very important, but not from a physics perspective. It is extremely important from a historical and philosophical perspective, because Bell's theorem finally convinced a large portion of the physics community that so-called hidden variables theories were incompatible with quantum mechanics. In this regard, Bell's theorem is important around quantum mechanics, but it leaves the physics of quantum entanglement completely unblemished. Our next brief presentation will be on the so-called EPR paradox.